Welcome to a new episode of our MBSE podcast. Today we are talking about Starforge. It's a very interesting tool, and as you will soon see, it's and here today. It's kann man nee.
No, life is life.
Life is life. Yeah, I've talked the whole week.
We were just talking in German the whole time.
I had workshop the whole day, the whole week. Okay, let's try again. So we are talking about Starforge, a great tool, and you will see this very soon. Well, we are in the MBSE podcast. The Starforge makes clever use of new features of SysML v2 in combination with open source tools. And it's an outlook into the future of engineering, I would say. And we got a special guest, Robert Carver. That's great. And we have another guest here, Johannes Gross. Both are from Planetary Utilities, which is the company behind Starforge. The first part of this episode is, as usual, we will talk about Starforge. So therefore, you can only listen to it. And at the end, we will show a demo. And of course, this only makes sense with the video version of the podcast. So yeah, welcome Johannes and welcome Robert. Great to having you here, and I hand over to Johannes to introduce yourself.
Yeah, Tim, thanks a lot. We were just chatting in German for half an hour, and so I think we all were surprised to switch into this other part of our brains that has the English language loaded. But it's great to be here. Thanks a lot for having us, for having Robert and myself. We are Planetary Utilities. We are a part of Planetary Utilities, and the name of the company really suggests we are building a utility company, and the scope is the planet, because anything you do in space is quite naturally of a global reach. And so that's the background on the name of the company, basically.
Cool. Robert, do you want to introduce yourself?
See you all again. Yeah, I retired last year from GPL and unretired a month later when Johannes called to action. Do you want to build a space company with me? And that included all the hardware, and now we're also building a digital ecosystem, a digital twin ecosystem that is Starforge to make that all happen. And here we are.
Very cool. Okay, so that means you are building a tool. It's a software tool. And maybe you can explain to our listeners a little bit more, what is Starforge exactly? How does it relate to MBSE and modeling in general? So that we get a better impression before seeing the demo later.
Yeah, so I think MBSE is really the term that came from the needs-driven side of the industry, right? Industry was working in these siloed tools, and the systems engineers had to connect all the data that were related but not related in the tools. And so they said, how can we connect them, right? Uh-huh. And so that's the MBSE term. Myself, I come from a little bit of a different school. In Stuttgart, we did research on graph-based design languages. And graph-based design languages kind of trace back to that vision from Star Trek, basically. When they go on the bridge to their computer and talk about the ship's configuration, and the computer is able to reconfigure, the machinery that runs this gigantic spaceship. That kind of gave us a vision of, yes, Christian is
well prepared.
He's showing his model of the spaceship. And so And so that, you know, that was kind of the origin of these design languages, where people were basically inspired to say design should be something that we can talk with the computer about, and that, you know, the computer can respond to and give us answers to our questions of how to design things. And so I think Planetary Utilities is really at this nexus between, and it kind of is represented also between the two of us. Robert is the practitioner, you know, the first user of SysML v1 on a really large project, and, you know, one of the drivers behind Magic Draw's Cameo development. And myself, I come from this, you know, more philosophical and abstract research world, where I built the first design language for satellites, and I had this tool 10, 15 years ago at my fingertips. And Starforge is basically now bringing this capability to the mass market.
And Starforge, it's more than the traditional MBSE modeling tools. No, but a traditional MBSE modeling tool is unfortunately very often another silo. No? So, but Starforge is more a platform. That's at least my understanding. So you're a platform for many different models. So can you talk a little bit more about that and the special role of SysML v2 on this platform?
Yes. So SysML v2 we really see as the platform technology in a way, right? The different engineering disciplines have all their individual data structures and models and methods. And SysML is one of the largest efforts of people coming together and saying, hey, we need a language that we can talk about all aspects of a system. And so it's, you know, it's not an implemented language. It's not something you can execute, because it's first and foremost our attempt at creating this language that can talk about all aspects of the system. And so Starforge is in some way a methodology layer, and it comes with certain ways of doing things to enable this, you know, this design language approach. And then on the other hand, its own architecture is really built as a platform, and openness is at the heart of it. And so SysML as a platform is basically enabled by this software architecture, so that we can create a platform where basically we can make engineering work together.
Yeah. So
Yeah,
maybe
I can add a couple of sentences there. Yeah. So when I joined Johannes 1.5 years ago, his first sentence was, "We're not going to use SysML at all." And then actually for like 10 months, I didn't open a model, and I coded mostly and tried to understand what we wanted, what his vision is, and how we can fit all that together. But at some point, SysML v2 emerged by itself, and I think mostly because of its API, standard API, that kind of changes that world completely, because now you can build web services around it. You can use it as interchange, exchange platform, and as integration platform across those disciplines, all those disciplines. And I mean, I've been using SysML and modeling tools for a very long time, and I'm now also teaching it. And it's just most of the time people discuss, or I discussed those in the past, how do we represent our domain or our application in the SysML model, right? That's a lot of time goes into that, which modeling concept, which arrow, is that the right relationship, and so on. And then there's all the tooling aspect. No, usually you have to click 50 million times to get a decent model. So we are moving that to the next level, right? We want to model and talk to our models and digital twins that are associated with the models in our application language, right? And the models, whatever they are, CAD, SysML, systems models, thermal models, they are created by the platform that is enabled by v2. I think that's this next step, right? I don't have to think about, and I don't want to think about that, at least initially, about all these nitty-gritty details of a particular language.
Yeah, that's amazing, because I did not know Johannes before this podcast. I know you, Robert, for quite a while. I know you have a new affiliation. And the more I hear you, the more I think that it fits perfectly to my own startup somehow. So let's go on. So you mentioned already that you want to gather information from different, I call it sources, from different domains. So you somehow also try to get information from the CAD or at least from the simulation world, right?
Yeah, so the way we organize that data is something we looked at, and I think the industry is slowly kind of catching up to this organization. So for CAD, on the system level, it's very important to be able to talk about assemblies. And the step standard, in its later revisions has, more of these provisions, right, to talk about assemblies and talk about kinematics as well. And then when it comes to simulations, CAD always comes first in engineering. So, the CAD kernel produces topology, right? And so that's, STEP is at the heart. It's very simple, right? It's bodies, faces, lines, edges, and points, right? So it's those four elements. And so once you have the result of the CAD kernel, now you can talk about materials, surface properties, and everything that defines your physics. And once you have defined your physics on base of your topology, now you can talk about the discretization, so how your solver will approach the problem. And so that is one of the basics of, our work, is organizing the knowledge in this hierarchical manner so that it gets reusable and repeatable and more flexibly usable. And then, as Robert said, we want to create a tool where the end customer of a system, right, the systems engineer, the project manager, can actually interact with with the digital twin as it is emerged during this design phase, and that's where we use AI as as an accessibility layer. And so in the long term, there will be power users that know how to create simulations and so on, but the front end user will be the vast majority.
Okay, cool.
So if I speak to Starforge and say, well, let's build a solar panel, there are two solar panels behind you. Let's create a model for a solar panel. How does Starforge knows what exactly I would like to have? So there are so many different solar panels. How does it work?
So that happens within the context of a specific design language. So if we are, for instance, in Starkit, our design language, that is the reason for why we're building Starforge and the driver behind it. We know that we may have a certain power system, and that power system may have a port for a solar panel that specifies what kind of solar panels we can attach to that power system. And so by having predefined interfaces, we can define the classes of objects that fit into those interfaces. And that way we get a flexible system where we can, combine hardware.
So you have something like a parts catalog in the background. So some
Exactly.
And if you replace Starkit with roof kit, then I create solar panels for my roof.
Exactly.
Okay.
Okay, cool. Now you both have a history in JPL, and from JPL there is also some open source software coming, which is also quite cool, and it's OpenMBEE. And we had Chris Delp in the podcast 2 or 3 years ago, and we talked about it. How do you relate to OpenMBEE?
Robert, you want to take that?
The initial, yeah. So I'm a co-founder of OpenMBEE together with Chris and a couple of others, and it's an open source, primarily an open source community, right? So it's a community of practitioners and some vendors that all share the same, say, pain. How do I create a corporate-wide model-based engineering environment? And those and it started out with an open source initiative at JPL, but meanwhile has grown in other and gathered other contributors as well like Boeing and Lockheed and Ford and ESO and others. And there's kind of one of the main projects of OpenMBEE is something which is called the MMS, the Model Management Service, that went through several architectural releases, and now the current one is called Flexo, because Chris is a fan of Futurana robots, and that is one robot there. It was Donbot before, and Execubot, Bot, and Bender, and so on. But that Flexo architecture is really a major revision, because it has a graph-based backend, and it provides a SysML v2 compliant API access point, among others, among like Sparkle or GraphQL. But v2 APIs is one, and that is and that Flexo is part of our architecture. So we integrate OpenMBEE Flexo to manage our SysML models and use it basically as the exchange hub for our v2 model. Johannes?
Yeah, I think that really sums it up pretty well. So for us, OpenMBEE is really the opportunity to leverage an open source project and be able to also contribute back to that community, because I think as engineers, we all share similar problems, and the landscape of tools that we need to integrate with is so huge that these integrations, they should happen in the open source space. That's really our view on this, and that's what we are working towards with OpenMBEE. We're also open sourcing some of our first integrations there. And yeah, we're also offering our Flexo deployment as a service. So if you want to try it out, you can contact us and basically get Flexo as a service spun up for your company, and try out those capabilities. And really, the way we deploy Starforge is based on these microservices. And so the way we see the future is, in the end, that you can mix and match those microservices to build up your application. So for instance, if you are a woodworking shop in southern Germany that makes furniture, in a specific way, you might have, code in your CAD tool that generates the layout of your furniture, and then you might want to have, a model management system in the background. You might have one for.
Oh,
Is it breaking up only on my side or also for
no,
you?
yes.
Same here.
You want to have an AI that your customers, and now you have to.
Let me text him.
Yeah. Yes.
Not the first time. Now he's back, I guess.
Yeah. So we missed the last 1 or 2 minutes.
No, not 2 minutes.
Oh.
The last 2 sentences.
I was just trying to make an example of how we see this evolve into a flexible.
The German woodworking was the last thing.
Yeah.
Oh. Well, I'm just seeing a future where we can build applications for specific, for specific needs out of building blocks in a way, and put them together so that you can build custom tools that are on the application level, that understand your domain. And we're of course doing space primarily, but I want to bring it down to much simpler examples, because I think will benefit a lot from this technology.
But the CAD model of this wooden furniture, is this then also stored in the MMS, or is this stored in my CAD modeling tool?
So I would always be, and at JPL as well, we've always been opportunistic about how to store, information. And the heart of it is really how to link it and how to manage it. So the digital thread is always, in German we would say Handwerksarbeit, in terms of you really need to look at the problem and look at how to solve the specific situation, right? Because the requirements can be so different. But in the case of CAD now, I think the one thing the industry is missing is, with STEP, we have a language that can talk about models on the result side of the kernel. We don't have a common language on the input side of the kernel, right? Because those were the UIs of the CAD tools up to now. And so we don't have good CAD AI yet because there's no training data. Maybe some startup will emerge and figure out a way of how to do it. But I think we need a common language on the input side of the CAD tool so that we can connect that to the system model better. That's my vision for that.
Okay. So what I understood now, the main audience for your tool at the moment is a systems engineer, but potentially could be any engineer or even more roles, right?
Yes, I think the tool will always be for engineers to really build these applications, but the platform itself, we're looking to basically fuel the integrated engineering future, where like OpenAI at its last developer day showed a little bit of that future on the commercial side, that you can talk to ChatGPT now and create a Figma presentation. But what about a physical artifact? If you can talk to GPT and it creates the solar installation on your roof, first in the digital twin sense, and then it finds an implementation partner who goes out and actually installs it on your roof, I think that's the future that we're looking at.
Cool.
And in Starforge, is it a one way? So I talk to Starforge and it creates or controls all the other models, simulations, CAD, and so forth. Or can it also go the other direction so that I continue working in the CAD model, do some stuff there, and then it goes back and integrates again somehow in the SysML world or in Starforge?
Oh, definitely. It's an open platform. So, the openness of your data is at the heart of it. So you can access the information that is in there in any way you want.
Yeah, and we have integrations and round trip workflows like that, where we extract information from CAD tools, the geometric information, and it will be stored as SysML in Flexo, in the repository, V2 repository, and then be used in other applications and other system engineering tools, and then it round trip in both directions.
Okay, cool.
So for all external modeling tools like CAD tools, also you have a representation also in the SysML model.
Yes. So the goal here is, and we have a working solution right now, but our goal is really to basically establish standards in SysML so that we might even be able to have something like step be expressed in SysML, and everybody can use it as a library, and the same way, I think a part of step is talking about assemblies and kinematics. That part we have in SysML right now already working, and so that we can now interface with the CAD tools. For instance, we have an integration with Onshape, which is a browser-based CAD, so you can import and export assemblies from into Onshape. But that's possible with CATIA, NX, SolidWorks, any other CAD tool out there.
Cool. Yeah, so before we are going into the demo, maybe we should describe a little bit what we will see in the next minutes so that our own audio-only listeners can have an impression and have an idea why it might be a good idea to switch to the YouTube video later on and have a look. So we talked a little bit before we went live, and you told us you are using Jupyter Hub as a preliminary user interface now, right?
Yes. So the tool right now consists of a Jupyter Hub client that you can access, and there's three core elements to this user interface. On the left-hand side, you have your chat agent, and then in the center, you have the code that expresses the current design, and then on the right-hand side, you have the views that project basically into the different engineering disciplines. And so the idea is, as of right now, because we're still building up these models and systems, you will have the AI that assists you in doing so, but you will also have access to the actual code so that you have control of the deterministic models of your engineering artifacts. And then the views are really the way you will interact with your system in the long run, so that the AI can present you with the views that you need to answer your questions.
Cool.
Okay, so I think let's start with the demo. So Johannes, you can share your screen.
Okay. Let me go over here and share this.
Yeah, it's there. So yeah, you can see it.
All right. So yeah, let's start with a SysML file. I think that's something, Tim, you have already used in your trainings, and we have already shown it other occasions. So right now we are offering the option down here to choose different agents. So our SysML v2 agent can now help us to build SysML models. So for instance, I would like to install some solar panels on my roof. Can you create a list of requirements in SysML? It's of course a really poor example, because I hope nobody will actually start with requirements. I just call their local electrician. But yeah, see here we get a list of requirements in SysML textual syntax, and they come comments and constraints, and so that is kind of the basic level of how we support SysML v2 and MBSE in general. So the SysML agent can help us, and for instance, if we have, for instance, here we have a little error. It says no type named integer found, because we haven't loaded the libraries yet. So we have a little button here that says fix in chat, and I hit that button and give it that error. And so the model understands, oh, I need to fix something. And so the validation results are fed back into the AI, and it can then go ahead and fix this. And now we have an import here of the ISQs. And so now we can use the integer variables, and the model is valid. And so yeah, this is a very straightforward way to create SysML models, and also to learn the language. So I could, for instance, say, please also create a part definition of the system with its components. And so that way, and I'm really making this up on the fly here. I haven't, this is not scripted. So I don't really know what will happen.
Johannes never scripts anything, which makes me always very, very nervous.
You learn a lot about your system.
Coming out of the shower, okay, let's go. But I think what is worth noting, I mean, this is let's say the underlying. I mean, I think Johannes is going to show the Starkit as well, which is like the cross-discipline part. But I think the thing worth noting is that there is like a tight integration of a network of chat agents that are working behind the scenes, that understand SysML v2 spec, the live model, and a formal live validation, right? So those things are key, right? Because the LLM will always produce something slightly different results, so you need something that validates that, so and we can feed that back. So I think that's a key element. And since it's integrated on the backend with the SysML v2 API, you can attach. I mean, we have in our integration Plexo, but you can integrate it with any. It's just one URL that you have to change to commit to some other v2 compliant backend, right? And it will work this way.
So I've switched over to a different window here now, and now I'm showing the next stage use case, basically. Once you have defined your your platform, how to use actually such a rich platform. So we're looking at the Starkit design language here, and we have a view over here that shows us a simple thermal model of our spacecraft. You can also see it behind me, one instance of that spacecraft. So we have a central backbone in this modular spacecraft, and then there's 1 cubic meter sized modules attached on either side of that backbone. So you have 7 on either side. You can have a total of 14 modules, and so you can build up your spacecraft with that. And so now I can go in here in this chat again, and I can say, please add a thermal module to the backbone. And the agent now knows how to use the design language in the background, and it adds that thermal module. And the only thing is I have to reload my page here because of some development. And now we have a thermal module attached to the backbone. And so now I can say, please deploy the radiator. And so as you can see here, we're crossing system boundaries in a way, right? First, I was on the top level and I was specifying what kind of modules I want to have. And now I'm talking to a function of the module, because the thermal module has the radiator, and that radiator can be deployed. And so
that's what we mean by operating at the application level, right? I mean, behind the scenes, all those models are created with well-defined patterns and libraries, and I don't have to know about it. It will make sure. I mean, I'm conversing with the AI agent, and it builds up behind the scenes the digital twin in a consistent way. But I don't have to remember all those details, how they connect. It will connect for the SysML part. It will connect the ports accordingly. It will create the interfaces to the thermal model. It will attach the things correctly in the mesh. For the cut, it will do something similar. So that and it will be all consistent across all disciplines. So that's what we mean by operating at the application level. And it's a combination, or let's say a collaboration of the AI that knows what is there, but doesn't do the engineering. The engineering is still done by the engineering tools, and that gives you this access to this big world of engineering landscapes.
And here you only add elements from a library, and for example,
exactly.
Now,
so
like to design a complete new kind of a solar panel. Can you also add this?
So basically, we're only showing this part right now, but that's basically the other part in a way. So it's kind of a new way of how to organize engineering work. In the end, we're already kind of doing it that way, but it's not as explicit. And so you have one place where you can build your individual components and define them. And then you have this other place where you combine that into a system, right? And so the interfaces between the components are basically the place where you specify what to do on the other side of the interface, so on these components. And so this approach is really very well suited for any kind of modular system where you already know your interfaces. And especially for space systems, from my experience, what makes us so slow in space when we develop large space missions is the creep of the interfaces often, because that's really the architectural changes, and they really reset every subsystem to redesign the subsystems. And so that's a big part of this approach here, is to have these interfaces that we know, so that we can now build these modules individually.
So with interfaces, you mean something like the electrical and mechanical interface between the solar panel and the backbone? Or did I?
Exactly.
Yeah, okay.
We're talking basically all physical exchanges, right? So that's another aspect of why space is really well suited for this, is because you really know fairly well how the systems couple. And so if you have a mechanical connection, an electrical connection, a fluid connection for thermal fluid, and a data connection, then you have everything you need on every subsystem and for every subsystem in a way. So this way we were able to decouple, the functions on a spacecraft, and we're able to create a really flexible system of how to quickly create new space systems. But for other industries and other applications, this might differ, and the way where you need the flexibility might differ, and so this is still like, I don't know the clear answer yet of how this will actually shape out, but our platform supports different architectures of that kind. So let me jump over here and also show, so now we have this geometric view of the spacecraft, and I added a power unit and a solar panel. I could go on. I think in the interest of time, let's jump over and see the other views. So here we have an integration with Tom Sawyer, and we can now load the SysML model of this spacecraft as this gets built up in the background while we were using the design language front end. So here we have the component of the nexus with its position, and then here we have the children components that represent the individual modules. And so you can see Rx, Ry, Rz, Tx, Ty, Tz are the rotations and translations of these modules. So that's really the geometry information of the CAD tree basically in there. And so now we can use that information to export it into other formats. And this time I'm going to go over here and show another view that we can have, which is actually, I think it was loaded in this window here. Let's find it. Here it is. So over here we have an integration with Sendero, and that's an orbit simulation. So here we can see one of our backbones with these modules loaded. And this model can also be generated from this, digital thread backbone that we are building out. And so this is a really interesting example, because before we were looking, at CAD and the geometric aspects of the mission, but now we also have generated, a representation of the power system and the behavioral aspects of the system. So in here we have, reaction wheels that actually control momentum gyros in this case, that control the attitude of the spacecraft, and they are affected by your choices of modules, by how big the moment of inertia of the spacecraft is, right? And so as we put together our Lego set of modules, that changes how the spacecraft behaves in orbit. But we can analyze all of this in the same tool and in one go. And so we can feed back that information onto the system level when we make our choices of which modules to use. So I can, for instance, go in here in the power system, and we can see, it takes a little second to load, but we can basically see here the representation of the system. Here's the electrical power flow, and here's the electrical power system state. And so this is all from this simulation now that we can see our digital twin is executing in orbit its operations, and we can look at the results and see how the system behaves under those conditions.
So you get all these, so in a minute, no? You type in and let's build this and that, and then poof, the model is there in SysML v2, you get the cut, you get the simulation, everything is integrated. So everything is built, the digital thread, everything is there.
Exactly,
right?
yeah. So, yes, so the models are really, of course, we have to go in and define all those aspects of these modules and do that on an individual level. But once they are built, now we can recombine them in all kinds of ways. And we can have, for instance, design where we add 2 power systems or even 4 power systems to those backbones. And now we have a really powerful spacecraft where we can use 100 kilowatts of power for an electric thruster, for instance. And so this really comes from my experience at JPL, where I saw that the cost of integration is so high. If we use in the space industry, for instance, if we use a reaction wheel from another company, we have hundreds of thousands of dollars on our own side of cost to integrate, just to integrate this, just to talk about the electrical interface, the thermal interface, the power interface, the software, how to use it. And so I realized this friction is really what limits our progress in space.
Yeah.
And so a tool where you can, yes, Robert, jump in.
I think no, because just said, okay, I have to have all these things predefined and so on. But I think this is a good, let's say, it enforces a good systems engineering practice, right? You want to define those elements that you're going to use to build your system. You want to define those interfaces. You want to define the architecture, right? And then you build your system and from that. And I think this is in particular fits very nicely with the product line engineering approach. If you have more variations, which is in our case for the spacecraft definitely the case, but it applies to many other domains as well. I think this kind of onboarding, okay, I add another element to my Lego set, right? With a defined interface, with defined behavior, with defined structure, and then I can just access it from my conversational digital twin and integrate it without, so someone can build those things and someone else can just use it, right? I think that brings another, let's say, nice new world to the system engineering population.
Yeah, especially when you're
some rigor.
Yeah, especially when you're thinking the digital thread over multiple domains. So yeah, I can really imagine what it means, because if you want to integrate some new whatever solar panel or whatever example, you might have a SysML model for it. You might have requirements for it. You have a CAD model for it. You have maybe a simulation model for it, and bringing these things together into this engineering world, and then have this Lego set, and then the different views. Yeah, that's a dream coming true. Yeah,
exactly. It forces you to make those things consistent, right? Break up those silos that we have, right? There's a million of those silos, but this approach kind of forces you to break them up and tear them down, right? And have all those relationships and the thread explicit, right? Not somewhere implicit in someone's heads or in a document.
But it also it also shows how important it is to have open interfaces. So with all these examples, I'm thinking of the SysML v2 textual notation, which is perfectly exchangeable. I'm thinking of FMI for the simulation part, of STEP for the CAD part, and so on. Without these standards, that doesn't work out.
It will be much harder, no? But yeah, I mean, FMI, FMU, SSP, V2, API, all those things, they play.
Cool.
Yeah, and as we are looking at this modular approach, a quick shout out maybe to any listeners from the academic world. We are very open to collaborating with universities and institutes that want to extend Starkit. Maybe we are open to sharing those models for academic purposes, because I think it's a great teaching tool to be able to go across the disciplines. If you really want to, create engineers that have a cross-discipline understanding and of the impacts of different decisions, I think you need a tool like that where you can actually look at the results. So just a quick shout out. Get in touch if you're interested.
Yeah, cool.
Yeah, you must not be a CAD expert, no? But you can see the output already in the CAD model and get some feedback from there, or the simulation, no? Also, that's really cool. Expert, yeah. And I assume you can also add other simulation tools or engineering tools to your platform if there's an open API, right? So it's not limited to Onshape and the other ones that you mentioned.
Absolutely. Yeah. I mean, the architecture that we have is fully flexible in that regard. It was designed and architected with that in mind, that we can integrate with, because there's already a million tools that organizations use, right? We want to integrate with them, and we designed it and architected in a way that first we can integrate, but also that it's scalable, right? Underneath there is a fully enterprise scale Kubernetes system that runs all those things, so we can deploy it as a SaaS or on-prem, right?
So while we were talking, I was actually just telling the agent to export our little design here with the two modules into Onshape. And so we could see how in Onshape the model was being built up. And we now have the fully resolved CAD model of this little spacecraft example. And so we can see all the details of the design and everything.
Cool.
Yeah.
And what was it before, the view in Jupyter Lab? This
other tool is called, so this one?
This is this is not Onshape then.
No, this is a much lighter weight graphics rendering of a mesh in the end. We use this for thermal simulation. So
okay.
This is yeah.
Yeah,
that's
cool.
a completely different model, right? There's a mesh underneath, and it's
okay. I thought that's
thermal analysis, but everything is consistent. No, the CAD model, the thermal model, the SysML model.
So the mesh model was derived from the
orbital
CAD
model.
Oh, okay.
That was built up as part of the conversation. So there's a bunch of code behind that also builds up.
Yeah.
Stuff. It's consistent with the V2 model.
But it gives you this one just gives you a very quick understanding if you're, in the mechanical domain. But really, as you build out a space mission, in this case, we have robotics that can do things on board the spacecraft, and all of this is really slated to be a service-based, marketplace of services, basically, a platform where many people can offer their own services. And so the different views also include, for instance, here a cost view where you can, get the breakdown of the cost of your modules and your backbone and your modules, and also a scheduling of, for instance, the robotics operations in this case for assembling the platform and what kind of resources are needed. So you can really go in all different aspects of business in that case, and connect all these aspects, so that if you redesign your mission or if you have a change in your plans, you can get all the results and all the views right away. For space missions right now, for instance, docking maneuvers are among the most expensive things, because people go through hundreds and thousands of simulations to make sure that their parameters are right, and because none of it is automated, So we're really working towards a system where we can automate the entire build pipeline in a, speaking in a software world here, to have basically nightly builds where, thermal simulations can run and things like that, to enable space missions in a much greater way.
Cool. Very, very cool. Unfortunately, we are running out of time. But yeah, maybe we can do in the future another episode about the tool and see how it evolves. Okay, so yeah, thank you very much, Johannes and Robert, for this. That was really, really interesting.
For having us. Thank you.
Yeah,
for the
thank you.
opportunity.
You're welcome.
So this is how the future of systems engineering should look like, or engineering in general.
This
It's
is
a
how
dream.
it looks like.
That's how it looks like. Yeah, right,
No,
right,
it's
right.
not even, it's not a dream. You
Yeah, it's
don't have
already
to wake
there.
up.
It's
already there. You don't have to wait. You don't have to wake up.
it's already there. Yeah, it's cool.
Okay.
Yeah, so this time we already know our next topic. We do not know the next date yet, but we know the next topic, and it will be about a project called, I don't know if it's spelled correctly, Ode for Hera. It stands for Open Digital Environment for Hybrid Electric Regional Aircrafts. The architectures, yeah. But it is for hybrid electric regional aircraft. So an interesting project. And well, why they are here or will be there in our podcast, because they use a lot of MBSE and also SysML v2. So we will talk with them about this topic in our next podcast in November, and we currently discuss with them about the date. So.
Yeah, I was on their conference or workshop last week in Hamburg, and it was really impressive to see what they are doing and how SysML v2 is already in use with different tools. It was really a nice meeting.
Okay, and with that, I would say we should not forget.
Trust us, we are systems engineers. Goodbye.
Okay,
Thanks, Johannes.
bye-bye.
Bye. Thank you.